Hello everyone and welcome to my workshop. So today I want to discuss a project that I've been working on for a few months now, and it actually involves the building of a system for depositing thin optical films. Now those of you who've seen my previous videos know that I'm making these tiny optical devices, and to take this a step further I need to be able to make stacks of very thin optical layers, and that's why I built this system. Now, it's actually quite a flexible system, and it's based on a technology called physical vapor deposition. It's not completely finished, it's actually sort of a work in progress, so I will build new aspects to it in the future. And now, as I said, it took me a few months so far to build this, so it's actually quite an elaborate project. I can't really go into every nitty-gritty detail here, but I'll just stick to the main subjects and show you around the machine, tell you a little bit about physical vapor deposition, and in the end hopefully we'll also deposit a thin film. Okay, let's just dive right in. So when discussing thin films for application in optics, the first things that generally come to mind are reflective layers, like those on mirrors, or anti-reflective layers, like the ones found on lens surfaces. But you can also think of layers that conduct light, or films that are fluorescent or electroluminescent. And one method for making these is by using physical vapor deposition, or PVD for short. This method is typically used to deposit films with a thickness below 250 nanometers. By the way, PVD is not only a key technology in optical coatings, but it is also frequently used in the manufacture of integrated circuits to apply all the layers that, after patterning, together form a microchip. The principle of PVD is actually really simple. You evaporate a material from a source and it deposits as a thin layer at another location, for example on the surface of a substrate. Now, to make sure that the molecules of the material go from source to target without first bumping into other molecules like the ones in air, you perform the process under a vacuum. Now, there are several methods that can be used for the evaporation of materials, and each method works best for a specific type of material. For example, magnetron sputtering is frequently used to deposit metals or metal oxides with fairly high melting temperatures. But you can also use a technique called E-beam evaporation, which uses an intense beam of highly accelerated electrons to heat up a material locally. And this method works really well for materials that have a relatively low thermal conductivity. But maybe the simplest way to do PVD is just to put your material in an electric heating element and then heat it up to a temperature close to its boiling point. And this is done by running a high current through a so-called evaporation boat. And I decided to use this method mainly because it's also very well suited to deposit organic materials, which is, for example, not really feasible with sputtering. However, thermal evaporation has a few limitations, mainly because of the temperature range for which it can be used. So here's a table with some of the materials that I've been planning to deposit, and it shows several materials in green, which should pose no problem for thermal evaporation. But for the ones in orange and red, we require higher temperatures than what you can comfortably achieve with thermal evaporation, either because they have too high a boiling point or because they are very bad conductors of heat. But even the materials indicated in green here require both materials being able to handle very high temperatures. Frequently used materials for making evaporation boats are tungsten or tantalum or graphite, and these all have melting temperatures in excess of 3000 degrees Celsius. But for some materials even that is not high enough to evaporate them at an acceptable rate. By the way, to deposit a layer, you don't need to go all the way up to the boiling temperature of the material. You just need a temperature at which the vapor pressure is sufficiently high. So let's take, for example, aluminum. It has a boiling temperature of around 2500 degrees Celsius, which means that the vapor pressure at this temperature is around 1 bar or 100 kPa. But you can also deposit aluminum at temperatures a few hundred degrees lower, although at a much lower deposition rate, because the vapor pressure is much lower at that temperature. The currents needed in thermal evaporation to heat up the boats are pretty substantial, generally above 100 amps. You therefore need a very good electrical conductor to connect the evaporation boats to the current source. But good electrical conductors like copper are also very good conductors of heat, so you need to cool the contacts, otherwise your setup will just melt after a while. For this, I made the contacts to the evaporator units from copper pipes that have cooling water running through them in order not to overheat. The copper pipes were bonded in a borosilicate glass disc, and the assembly could be mounted inside a single vacuum feed. And this allowed for the construction of two water-cooled evaporation sources within a very small footprint. As an electric current source, I used a low voltage, high current transformer, and the transformer current is controlled by a thyristor. I also made a small remote control to be placed next to the chamber to control the thyristor while being able to look in the evaporator chamber. Thermal evaporation usually requires high vacuum conditions. First, because the mean free path length, so the average length that molecules or atoms can travel before they bump into another molecule, has to be quite long, preferably much longer than the distance between, let's say, source and target. And also, you want to have as little oxygen and water around while you are depositing, as these molecules can generally quickly react with your sample. So you need a vacuum level better than 10e-5 millibar, which by the way is 100 million times lower than normal atmospheric pressure. To achieve this level of vacuum, two different pumps are needed instead of just one. And as a basis for my vacuum system, I used a defective Balzer's plasma cleaner, which I bought a few years ago as scrap. It contained all the vacuum equipment necessary for this project, like a rough pump, a high vacuum turbo pump, and a set of vacuum valves. And these valves allow for accessing the chamber without the need for closing down the complete vacuum system each time you want to take a sample out. Unfortunately, the original chamber of the plasma cleaner had been damaged in a previous life and was leaking. Also, the shape of the chamber was very impractical. It was way too large and it had a very limited number of feed-throughs. So I decided to build something much smaller based on some other vacuum surplus that I had gathered over the years. The system I designed basically consists of three individual parts. A bottom plate that holds all the vacuum equipment and evaporation sources and a plasma generator. On top of that is a cylindrical chamber with several feed-throughs. And to close the chamber off, there's a lid that contains an optical window, a rotation axis and quite a few electrical feed-throughs. The parts can then be stacked together by using some homemade large vacuum rings. Now, the chamber cylinder and the lid are basically adaptations of some surplus parts, but the bottom plate is something that I designed specifically for this system. It's made of 12mm thick RVS plate in which I had some holes made and to which I added a few vacuum connections using TIG welding. Now, I must admit that I'm far from a professional TIG welder, and to even master it to an elementary level took me several hours of practice and watching countless videos about it. During that time I made what could probably be considered the ugliest welds in the history of ugly welds. But after some time I sort of got the hang of it and then felt confident enough to make my first parts. And that was when I discovered that there is a big difference between just welding things together and creating high vacuum compatible welds. Because even welds that look quite clean and solid can still contain significant leaks. Fortunately, I was able to track them all down using compressed air and a bit of soap solution. They could then be repaired by remelting the metal at each point of failure. So after welding, I had to make the contact surfaces between the three parts a bit smoother. The RVS plate that I had bought was relatively rough and needed to be flattened and polished before it could be used to make vacuum compatible seals using the large rubber sealing rings. And this required several consecutive steps of grinding and polishing before the contact surfaces had an acceptable flatness and smoothness. Now, during the construction of the system I actually made a few serious mistakes that took me a lot of time to correct. And one of these errors caused a protective metal filter to end up inside the turbopump while running at 50,000 RPMs. And this happened because I placed an aluminum spacer ring on the wrong side of a valve. So due to this incident, the top blades of the turbo got kind of damaged, and it also generated a lot of microscopic aluminum dust that spread over a large part of the vacuum system. So I had to take everything apart again, repair the turbo, clean the complete vacuum system, the works. But in a sense, I had also been very lucky, because this incident could easily have destroyed the turbo or even caused bodily harm, because a fast spinning turbo contains a lot of kinetic energy and can easily start flying around the room when that energy is suddenly released by a crash. From an Arduino and a power relay card, I made a controller for the valves and the pumps. And as you can see, it currently looks a bit hobby-bobby, but you know, who cares, it works. Unfortunately, the display broke down after a few days, so that's another repair. Another piece of functionality is a rotation mechanism that can either be used to achieve a better layer uniformity or can serve as a shutter. An optical window allows for monitoring of the optical properties of the layers while evaporating, and for configurations where that's not really feasible, for example because the substrate is non-transmissive, I also added a quartz microbalance to the chamber. And this works by measuring the resonance frequency of a small resonator circuit, which incorporates a quartz crystal. Now, the quartz crystal is placed inside the chamber in such a way that it is exposed directly to the evaporation process. So during the evaporation of the layer, the mass of the crystal increases, which decreases its resonance frequency. And by very accurately measuring the shift in the resonance frequency, we can therefore determine the rate of deposition. Now, I first tried if I could use some very cheap quartz crystals like the ones used in electronics by making a small modification. And while this is certainly possible, I built a configuration such that unfortunately the resonator circuit did not survive the plasma cleaning inside the chamber. So I guess there's another repair again. In addition, I have to buy some official crystals that are used in deposition monitors. I will discuss one more feature here, and that is plasma cleaning. So cleaning of your substrates in solvents like isopropanol usually leaves behind a thin layer of organic residue on the surface. And this can prohibit good adhesion of your deposited layer. Now, a very convenient and effective way to remove organic contaminants is by using plasma cleaning inside the chamber, so right before the actual evaporation. With plasma cleaning, we generate highly energetic ions and radicals in a low pressure gas. And these can quickly react with the organic residue to form gas phase reaction products, which can then be pumped out of the chamber. Now, plasmas can only be created in a specific pressure range, so we also need a way to regulate the pressure in the chamber, for example by controlling the inflow of gas or air. And since creating plasma requires high voltages, you also need an interlock on the chamber if you don't want to die during a moment of inattention. So the electrical source for plasma cleaning was made from a standard microwave transformer, which generates about 2 kilovolts AC. So the power is regulated by inserting a simple power regulator on the line side of the transformer. I also made a special vacuum compatible feed for the high voltage of the plasma source. So the feed-through had to be firmly insulated from the chamber because of the relatively high powers and voltages involved. The plasma is made from air that is let into the chamber at a very low flow rate, and I used a mass flow controller salvaged from the Balzers unit for this. I also made a control unit to regulate the flow through the mass flow controller. So this is what the plasma looks like in operation. It's sort of a bluish pink due to the presence of mainly nitrogen and oxygen. And it seems to work very well for removing organic contaminants in just a few minutes. The system is now sort of working, so let me just show you what a quick evaporation looks like. In this case, the deposition of a thin layer of silver. So in order to get a good view, I temporarily replaced the standard lid with a borosilicate glass disc. Pumping down to the 10E-5 range took about an hour, and it mainly takes so long because of the water adhered to the chamber walls. So after the pump down and the plasma clean, I can run a current through the tantalum evaporation boat that contains a few small grains of silver. And here you see a top view of the evaporation boat through a glass substrate. So when heating up the boat, you first see the silver melt, and then after only a few seconds it starts to evaporate. And since we're looking through the substrate, you see the radiation from the evaporation bath slowly diminish due to the decreasing transmission of the silver layer that's being deposited on the sample. Now, at the same time, you see the back of the smartphone with which I'm filming this coming into view because of the increased reflection of the layer. And this is the result, a nice reflective layer of silver on a glass substrate. Now, silver generally adheres very badly to glass, so just to be sure that the plasma cleaning works well, I repeated the same process but then using chromium instead of silver, and chromium adheres very well to glass. Now, in this case I could comfortably perform a tape test multiple times without any layer delamination, which means that there is indeed very good adhesion. Anyway, I will stop here because this machine is basically just a tool to make optical devices and it's not a goal by itself. And as I said in the intro, it's not possible to go into every single detail here. But if you have any additional questions about PVD technology or this machine in particular, please ask them in the comments. Also, I will elaborate a bit more on specific aspects of the machine in upcoming videos when making optical layers. Okay, that's it for this video. I hope you enjoyed it and maybe see you in it.